These notes are for AP Calc AB. This is objective 8.2, which is more with the natural log of x function that we were working with in 8.1. So in this set of notes, we're going to be doing two parts. In the first section, we're going to look at problems from units 2 and 3. And just types of problems that we did then, only now we want to involve the natural log of x function. All right, so in that section, in Unit 2, we started writing equations of tangent and normal lines to functions at specific values. So you'll want to remember that the two things you need when writing the equation of any line is a point and slope. So right now we've been given the x value 1 to find our point. We need to plug 1 into the original function. So f of 1. Natural log 1 minus 1 cubed, 0 minus 1 is negative 1. So my coordinate pair, 1, negative 1. Because we're looking at the tangent line, the slope of the tangent line is our derivative. So we'll start with the derivative of f. So the derivative of natural log x, 1 over x, minus the derivative of x cubed, 3x squared. From here, we want to evaluate our derivative at x equals 1. So f prime 1 divided by 1 minus 3 times 1 squared is 1 minus 3, or negative 2. Now that we have our point and slope, we can write the equation for our tangent line. All right, so we'll use our point slope formula to write the equation. We want to do y minus our y coordinate, negative 1, is equal to the slope times x minus the x coordinate. So we have our tangent line. For the normal line, the only thing that happens, since the lines are perpendicular to one another, is our slope changes to a positive 1/2. And we have our two equations. So I hope you remember those problems from objective 2. So we're going to look at something from objective 3. All right, so finding relative extrema, points of inflection, intervals where a function increases, decreases, or is concave up and down, all comes from our first and second derivative tests. The thing you want to watch out for is a lot of the time we're working with very nice functions like polynomials, and they tend to work out just so nicely because they have a domain of all reals. When you're working with trig functions, some trig functions like sine and cosine also have a domain of all reals, but if you're working with tangent or secant, you'll want to look out for where those asymptotes occur, right? our domain is not all reals anymore. Same thing happens with a square root function. You don't have a domain of all reals. Same thing happens here with a natural log of x function. So a real easy thing to remember is that you can't plug in 0 or any negative number. So anything inside of a log must always be positive. And so the domain of this function is 0 to infinity. So why do I need to know that? When I do my first and second derivative tests, those are number line tests. And knowing this means that my number line should only exist from 0 to infinity, and I should only be testing things within that domain. So that's why we want to make sure that we point that out anytime we start a new problem with number line tests. So always take a look at the domain. With that, we can start in on our derivatives. All right, so my first derivative is 1 over x minus 1. What I'm looking for right now are critical numbers. So you always want to look for anywhere where your function, your new one here, does not exist. And that would happen when x is 0, but I already know x can't be 0. And then I want to set it equal to 0 and solve. So we end up with the critical number 1. So we're going to go ahead and put 1 on our first derivative number line test, which only exists from 0 to infinity. We mark 1 on here as the 0 of our derivative, and then we'll test those intervals. So if we plug in a number like 1/2 for x, 1 divided by half is 2, 2 minus 1 is a positive. If I plug in any number bigger than 1, I end up with a number like 1/2, 1/3, 1/5, minus 1 will always be a negative. And so we do our interpretation here. So when my derivative is positive, I know that the function g is increasing. So 0 to 1. Decreasing where the derivative is negative. And then that sign change from a positive to a negative, or my function increasing then decreasing, tells me that I have a relative maximum. So we can say at x equals 1, if we wanted to know the coordinate pair, we would plug 1 back into our function to find that coordinate pair. So these are the values I have for my first derivative test. So let's take a look at our second derivative test. So I want to basically do the same thing. 1 over x, or x to the negative 1, has a derivative of negative 1 over x squared. The derivative of negative 1 is 0. And again, g double prime does not exist when x is 0, but I don't have to worry about that because I'm already not including it in my domain. If I try to set this equal to 0 to find any numbers to test over, you'll find that your fraction never equals 0. So I have no test values. Like last time we had 1 to test on either side of. This time I don't have any value to test over. So on my number line here, there's nothing to mark. We just plug in any number we want to our second derivative. So you can plug in 1/2, 1, 3, you can plug in pi, 17,000. It doesn't matter what you plug in. You will always end up with a negative 1 over whatever, so a negative number. My second derivative tells me the concavity. A negative second derivative tells me that my function is always concave down. And without a change in concavity, there is no point of inflection. All right, so that is example 2. So one more thing that we did right at the end of Unit 2, and then we picked up again in Unit 4, was implicit differentiation. All right, so an implicit function is when your x's and y's are really just all mixed together on the same side of the equal sign, or maybe even a few things on one side or the other. We just don't have an explicit function like in the previous example, y versus x's on the right. So here we want to take the derivative with respect to x, just like we typically do. Anytime you take the derivative of an x term, you're followed by a dx dx, which is 1. Anytime you take the derivative of a y term, what follows is dy dx. And that's what we want. That's what we're trying to find. So count up your y terms. There are 2. For each y term, you should end up with a dy dx. So 2 y's means I should get 2 dy dx's. So the derivative of x squared will give us 2x dx dx, which we don't need to write. The derivative of 5y, 5, followed by dy dx. Anytime you take the derivative of a y term, you'll get a dy dx. Next, minus 2 times the derivative of natural log y, 1 over y, dy dx, is equal to 0. Our goal here in solving for dy dx, if there's 2 of them, we want to isolate them so we can factor it out. So I'll start by subtracting 2x over to the right side. That isolates the dy dx terms, so I can factor out dy dx from the 2 terms. That's going to leave me with 5 minus 2 divided by y. To finish solving for dy dx, we need to divide this term over. And then we can't leave our answer as a complex fraction. So we're going to multiply everything by y. And then we have just one too many negatives. I'm going to take the negative from the numerator and distribute it into the denominator. So what I'm doing is just pulling that negative out front in front of the fraction as a whole, and then I'm going to distribute it into the denominator. So the top will remain positive 2xy. The bottom, you'll switch signs. And anytime you can do that with a negative, so I've gone from having 2 negatives in my answer to 1, that's simplifying it, and you'll need to do that. All right, so that is all review stuff from units 2 and 3 using natural log functions. So part 2 of our notes is going to be similar to what we were doing in objective 1. So taking a derivative, and the function looks like this. So you'll see it's quite like a messy function. You have x times x minus 1 to the power 3/2, a product with a fractional exponent divided by the square root of x plus 1. If I start taking the derivative here, like we would have learned in unit 2, you'd start with your quotient rule, low d high, minus high d low, and so on. When you get to the derivative of the numerator, you'd have to use product rule. When you get to the second term within the product rule, you're having to do the chain rule with a fractional exponent. It's not very pretty. So we're going to use something here called logarithmic differentiation. So you'll notice that for the problems like this in the book, it'll say use logarithmic differentiation. What this means, you'll notice there's no log here. When it says this, it means that you are going to introduce the natural log to both sides, or take the natural log of both sides. So that's going to be like this. The natural log of y on the left is equal to the natural log of all of this on the right. So we might not be the biggest fans of logs from what we remember last year, but why would we want to do this? Quite a messy derivative without it. Now that I have introduced a log here, I can actually use my log properties to split this up. I can simplify this because now it's part of a log. You do have to deal with the fact that the left side's also a log, but we'll get to that in a minute. So I'm going to start by simplifying on the right side. So I have the natural log of y is equal to, we'll start with the quotient, natural log of our numerator minus the natural log of our denominator. Next, we'll take the product inside here and split it up. So product to sum. So this is the property that said natural log A times B. So x will be my A term, the x minus 1 will be the B term. The last term will just bring it down. And I'm also going to rewrite it as x plus 1 to the power 1/2. So almost ready to take the derivative here, but there's one more log property I can use, which was the power property. So I'm going to bring my powers in front of each log as coefficients. Any of the properties you can handle doing at the same time. You don't have to take your time writing them out in so many separate steps. So if you feel comfortable separating more all at once, go ahead. Just watch out for any negative signs with addition signs. You might get mixed up just doing too much at once, so be really careful. At this point, there's no more log properties we can use, and we're ready to take the derivative. So it's just going to be derivative of each individual term. So a much nicer derivative to take. So over here, just like with implicit differentiation, the derivative of natural log y is 1 over y followed by dy dx. So we actually did that in example 3. There was just that -2 coefficient. We did the derivative of natural log y, 1 over y, and we followed with dy dx. So it's that same idea here on the left. The right side, derivative of natural log x, 1 over x, plus a coefficient 3/2, derivative of natural log x minus 1, so we want to do 1 over what's inside, times the derivative of what's inside, which would be 1, minus 1/2 times the derivative of this natural log, 1 over x plus 1, times its derivative, 1, so the derivative of what's inside. So this is what we have for a derivative, a much easier derivative. And that was the only calculus we had to do, just the derivative with a log, so that new derivative rule. The only thing we have to do now is get dy dx by itself. So I can't leave this as my answer. I need to solve for dy dx by getting rid of the 1 over y in front. So to do that, we just need to multiply both sides by y. So we want to multiply this whole right side by y. The y over y reduces and leaves you with dy dx. On the right side, we have 1 over x plus 3 over 2 times x minus 1. So I'm just starting to push my fractions together. Minus 1 over 2 times x plus 1 and at the end times y. So I don't want to write times y because I know what y is. So right back here at the beginning, we're going to substitute that y is x times x minus 1 to the power 3/2 over the root of x plus 1. And that is it. You don't do anything else with this problem. You don't need to worry about a common denominator inside here unless you really want to do that. And you don't need to do anything with distributing this term inside at all. So avoid doing anything like that. So it's really just a bunch of log properties of derivative and cleaning it up. Okay? So that's what it means to use logarithmic differentiation. You put the log on both sides, makes for an easier derivative. Okay? So we're going to see one more example of this. All right, so it says y is equal to sine x to the power x. So even if you didn't introduce a log to both sides, last time you had an option. You had a way of taking this derivative, quotient rule, product rule, some chain rule. But this problem, it's not sine to the power 10. It's not a known exponent. It's a variable in the base and a variable in the exponent. The only method you have for taking the derivative here is by using logarithmic differentiation. So we'll make that note. We're going to take the natural log of both sides. Okay. The reason why it works here and helps us is I can use a log property. The only log property that you can use here is that power rule. We're going to use x as the exponent of sine. We'll bring x in front of our natural log as the product, kind of like a coefficient would, right? We usually know have a number here as this exponent. It's just a variable. So we'll bring x in front. We have the natural log of y is equal to x times the natural log of sine x. So we just brought this x in front. That's going to allow us to use the product rule here to take our derivative. So before we didn't have a way to take the derivative. By introducing a log, I can now use the product rule on the right. So I'm going to give you a really big hint here. That anytime you have this variable base and a variable exponent, you're going to use logarithmic differentiation. Again, number 4, you kind of had an option, but it's better with the logs. This time you don't have an option. The only way to take the derivative is to introduce those logs. So, do you have y equals a variable to the power of a variable? If so, introduce natural log to both sides. Then you'll use your power property to bring the exponent in front. From there, it's your product rule. So you'll see problems like this over and over throughout the unit. So we want to finish the problem here by taking the derivative of each side with respect to x. On the left, we have the derivative of natural log y, 1 over y, for the derivative of any natural log, 1 over what's inside, times the derivative of what's inside. So that's our dy dx. On the right side, we have our first term and our second term, so we use our product rule. First times the derivative of the second. So the derivative of our natural log is 1 over what's inside times the derivative of what's inside. So the derivative of sine is cosine. Okay, so that's 1 d2 plus the second times the derivative of the first term. So derivative of x would just be 1, and we don't need to write that. So besides simplifying cosine over sine to cotangent, we just need to multiply by y over here to the right side like we did last time. So that reduces the y's. You're left with dy dx, which is what you're solving for, is equal to x times cotangent x plus the natural log of sine x times y, which was sine to the power x. And that's your answer there for number 5. So these derivatives are not going to be really pretty. They're going to be kind of complicated. You're just going to leave it in that rather messy expanded form. Anything simple like cosine over sine, you should simplify. If you ever end up with like an x divided by an x, you should always simplify things like that. And then just try and look out for this. You'll see more problems like that on the objective sheet. So on objective 8.2, it should be extra problems 1 and 2. Should be just like this problem here. All right, and that is the end of our notes.